Calculus, video 23, higher order derivatives. So sometimes after we find the derivative, we want to take the derivative again, right? We get the derivative, we want to do it one more time. We want the derivative of the derivative. This is called the second derivative. The derivative of the derivative called the second derivative. So a little bit of notation here. If you have your original function f of x, so function, the derivative is f prime of x, derivative. If you want the derivative of the derivative, you get what is called the second derivative. And we label that f prime prime of x. You can keep going. You don't have to stop here. You can find what's called the third derivative. That would be f prime 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 of x. That would be the derivative of the derivative of the derivative. Again, this goes on forever. You can find the fourth derivative. But eventually, we kind of run out of room for primes, and all the primes kind of look alike. Like if you have 7 of them, it's hard to count them sometimes. So we stop putting primes after 3, the little slash marks up there. Instead, once we get to the fourth derivative, and you could actually do this earlier, for our notation looks like this. We put number 4, but in parentheses, to denote that we're talking about the derivative. What that's saying is I have 4 primes here. It's f prime 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 of x, or the fourth derivative of x. I very easily could have done this way back up here, and for the second derivative, put f2 in parentheses in that kind of exponential spot up there of x. It means the same thing. Okay, so those are what are known together as higher order derivatives. And it does not have to stop at 4. You can have f, the 14th derivative of the function. Okay, more notation. Or, what if we want to use the dy dx notation? Right? So the function is y. So y is like our function or equation. Dy dx, that is the derivative. The second derivative, right, the notation for the second derivative is this. It's the second derivative of the function dx squared. So it's d squared y over dx squared. And just for notation purposes, this is how we write it. You want to think of that, however, as like dx in parentheses squared. It's squaring the dx, it's squaring the change of x term, as opposed to, it's not the x that's being squared. We don't write those parentheses, but that's how you should think of it as. The third derivative is d3y over dx3, and so on and so forth. The fourth derivative d4y over dx4. And the nice thing about this notation is it doesn't change form, once you get to the fourth derivative. Right, the first derivative, the second derivative, the third derivative, the fourth, they all have the same notation, right? D to some power y, dx to that particular power. And you'll find the further into math, the further into physics and engineering you get, the more we will end up using this notation as opposed to the f prime notation. It just ends up being more useful and easier to write things with. Okay, so those are the notations. Let's try some examples. Example. Let's go with, let's find f prime of x, f double prime of x, f triple prime of x, the fourth derivative of x for the functions. Find this, and that. Let's have our first function be f of x equals 1/6 x to the third minus 6x squared plus 5x minus 7. If you want to, right, pause the video, see if you can work through this on your own. I'm going to go ahead and work through it. F prime of x, the first derivative. We can use the power rule for each of these. So it's 1/6 times 3. 1/6 times 3 would be 1/2. Subtract 1 from the exponent, so 3 minus 1 is 2. Minus, bring the 2 on the 6x squared, bring the 2 down, so it's minus 12x to the first. Plus 5, bring the 1 down, now it's x to the 0. Anything to the 0 power is 1, so just plus 5. Alright, that is the first derivative. Let's take the second derivative. We'll just do the derivative of the derivative. So I'm looking at 1/2 x squared. I'm going to bring the 2 down. 1/2 times 2 is 1. And 1 x to the power of 2 minus 1 is 1. And then minus 12. Bring the 1 down. 12 times 1 is 12. X to the 0, so that's just 12. The third derivative. The derivative of x, we'll bring the 1 down, x to the 0, x to the 0 is 1, so it's 1 times 1 is 1, and the derivative of 12 is 0, because 12 is a constant. I think I failed to mention this, but in the first derivative, the 5, right, the derivative of 5 is also 0, because 5 is a constant. And then finally, the fourth derivative of the function, the derivative of 1, 1's a constant, so the fourth derivative would be 0. I asked for the fourth derivative, but let me just take it one step further. The fifth derivative, the derivative of 0 is 0. 0 is a constant, its derivative is also 0. What you're thinking there is 0, right? If you graphed 0, 0 is the line horizontally right here. What's the slope of the line at every point? The slope of the line is 0, therefore its derivative function is always 0. Good, let's try another. How about f of x equals e to the x? Again, pause the video, work through it on your own. Let's find the first 4 derivatives. So I'm going to switch notations here just to practice. The derivative of e to the x is e to the x. The second derivative of now e to the x, the first derivative, is e to the x. The third derivative, still e to the x. The fourth derivative, oops, I said third and I did not write 3. The third derivative was e to the x. The fourth derivative is e to the x. The fifth derivative is e to the x. The nth derivative is e to the x as well. This will continue on forever. The 43rd derivative of e to the x is in fact e to the x. Okay, so how about maybe a more interesting problem? How about the derivative of, let's say our function here, h of x, is 2 square root of x, which we will of course rewrite as 2x to the 1/2 to get that rational exponent. Let's find the first 4 derivatives here. And again, pause the video, right? Try it out on your own, come back to it. The derivative of 2x to the 1/2. Again, using this other notation just to get us more used to it. We're going to bring the 1/2, this is power rule, bring the 1/2 down, times 2 is 1, so I get x to the negative 1/2. The second derivative, so this would be the second derivative of 2x to the 1/2. That's the same thing as the derivative of x to the negative 1/2. And so the second derivative of the original function is the same thing as the derivative of the derivative, which is negative 1/2 x to the, what is negative 1/2 minus 1 would be negative 3/2. All right. The third derivative of 2x to the 1/2. That's the same thing as the derivative of the second derivative, right? The derivative of the thing we just found, the negative 1/2 x to the negative 3/2. We'll bring the negative 3/2 multiplied by negative 1/2. That is positive 3/4 x to the subtracting 1 gives us negative 5/2. And the fourth derivative of 2x to the 1/2 is the derivative of the thing we just found, the third derivative, 3/4 x to the negative 5/2, which is, bring the negative 5/2 down, so that's negative 15/8 x to the negative 7/2. And I like this problem. Let's pause and just kind of think about the problem. We got the answers, but let's dig a little bit deeper, because what we're going to see is we're going to see some patterns come about. Right? So we started with 2x to the 1/2, then we got 1x to the negative 1/2, negative 1/2 x to the negative 3/2, 3/4 x to the negative 5/2, negative 15/8 to the negative 7/2. One of the patterns is, and this one should be recognizable, we're subtracting 1 in the exponent every time. 1/2, negative 1/2, negative 3/2, negative 5/2, negative 7/2, negative 9/2, 11/2, negative 13/2, negative 15/2, right? It's going to keep going. A pattern you might not see is check out the denominators. So starting here with the first derivative, the denominator is 1, right? 1 over 1 is 1. Then it becomes 2. Then it becomes 4. Then it becomes 8. Next time it's going to be a denominator of 16. And we can see that because every time we're multiplying it by something over 2. Something over 2, because the denominator of that exponent is 2. So it's going to be something over 16, something over 32, something over 64. We get this pattern. The numerator, right, you're multiplying it by, the first time by negative 1, the next time by negative 3, the next time by negative 5, the next time by negative 7, right? You're multiplying it by well, 2, I guess, less than the previous numerator, negative 3, negative 5, negative 7, the next one times negative 9, the next one times negative 11. And because you're multiplying by a negative, what's happening is the signs are changing, right? Starting with the first derivative, we had a positive x to the negative 1/2, then a negative 1/2, then a positive 3/4, then a negative 15/8. When I multiply that by negative 7/2, that coefficient is going to be positive. The next one's going to be negative, then positive, and negative, and they flip back and forth like that. Right? And those patterns end up being important for us later on. Okay, let's do one more. One more, and we'll call it good for this video. How about k of x equals 4 over x? Hopefully, when you're thinking about this, the first thing you're doing is rewriting that as 4x to the negative 1. Then you're taking the derivative. Again, pause, try it on your own, come back. All right, so let's go back to the original notation, just to kind of use both. K prime of x will bring the negative 1 down, so that's negative 4x to the negative 2. K double prime of x, negative 4 times negative 2 is positive 8x negative 3. Third derivative, negative 24x negative 4. And the fourth derivative, 24 times 4, was that 96, I believe? 96x to the negative 5. Similar patterns arise here, where the exponent is just decreasing by 1 every time. Negative 1, negative 2, negative 3, negative 4, negative 5. The signs are switching. We get negative, positive, negative, positive, negative, positive, right? Because we're multiplying by a negative number. It's coming down from the exponent. And we actually get kind of an interesting pattern, which we'll talk a little bit more about in the coefficients as well. Notice that each time you're multiplying by 3, then by 4, then by 5, you're multiplying by 1 more than you had, like one higher number, in this case more negative number than you had previously. Okay, that is all for this video on higher order derivatives.